So welcome everyone. Thanks a lot for being here. If you're joining us for the very first time, this is another training session from the Network of Resources webinar series. So each week we have a webinar session that introduces you or dives deeper in one of the cloud platforms or services that are available in the Nord portfolio. So today we're very happy to have Guna and Constantin from Brockman Consult for a deep dive in XCUBE ecosystem, which is an open source software package for generation, management, and exploitation of EO data cubes. So I will hand it over to you, Constantin, in a bit. For the participants, please feel free to write to us your questions in the chat. We will take them as we go along or at the end of the session where we have a Q&A session. And as usual, at the end, my colleague Federico will present to you the Nord portal and the sponsorship process if you want to request XCUBE services. So the floor is yours, Constantin.
So you can see my screen, right?
Yes.
Wonderful. So yeah, hello everybody. I'm Constantine.
Maybe if you can zoom in just a bit more, at least from my side.
Zoom in. Okay, make it bigger.
Yes.
Wonderful.
That's perfect.
Okay, we also like that. Okay, so I will give you a little overview of the XCUBE ecosystem at DeepESDL. So DeepESDL stands for Deep Earth System Data Lab, and it is an ESA-supported platform which provides modular services to implement processing workflows based on EO data and models. And yeah, ESA supports the usage of DeepESDL by sponsoring service subscription via the network of resources. The central component of the DeepESDL is the DeepESDL hub. So it's a Jupyter hub, which gives the user an environment where the user can set up a science project and collaborate effectively within a team. So what you see here is that kind of Jupyter hub. Of course, you could also just use XCUBE as an open source Python package and install it according to the XCUBE documentation. Regarding XCUBE, so XCUBE is an open source Python package and a toolkit which allows to provide which allows you to take EO data and put it in an analysis-ready data cube, basically. So that data cube will then follow the CF convention that then can be analyzed and published in the cloud. On the side, you have a viewing application, which is called XCUBE Viewer, and in there you can visualize and also explore that data cube. So in the beginning, I will give you the main features of XCUBE, which is basically a theoretical introduction to XCUBE, and then we dive in and we execute some code in a real-world application. So XCUBE basically has 4 pillars. The data store, which allows you to access data. Then the data processing, which converts the EO data source into a self-contained data cube. And then we have the server, which is a set of RESTful web APIs, which are used to manage the data cube. And then we have the viewer for the visualization. So regarding the data store framework, it basically abstracts away the individual data sources and the protocols and formats, and it puts each data source in an X-array dataset with multiple geophysical variables, and each variable can be n-dimensional. So it basically gives you a simple and consistent Python interface. If possible, you can not only access the data, but you can also write back data for certain data stores, and the entire framework is pluggable. So each time when we have a new data source, we can develop a new plugin basically to support that data source. So XCUBE comes with 3 data stores as a default. The first one is file, which represents your local file system. Then we have S3, for AWS's free object storage, and memory, which mimics the in-memory file system. And each of them can open netcdf, SARS, TIFFs, GeoTIFFs. There are also some other formats, but they're dependent on the type of data store you have. Now we come to the plugins which are available so far to support several cloud-based data ecosystems. So for instance, we have XCUBE SH, which supports the Sentinel Hub Cloud API. Then we have XCUBE SMOS, which is the link to the ESA SMOS Level 2 data, the XCUBE CCI, which is the links to the ESA CCI Open Data Portal, the XCUBE CDS, which is the links to the Copernicus Climate Data Store. Then we have XCUBE CMEMS for the Copernicus Marine Science, and currently under development is XCUBE Stack, which will give the link to data resources organized in a spatial temporal asset catalog short stack. Regarding the data processing, so basically the data processing is applied such that when you have opened the data, you will transform the data into a self-contained and self-described data cubes. And here are some examples which are implemented in XCUBE. For instance, resampling. That means that you can project your data to another projection, or you can resample your data to another spatial resolution. Then rectifying is shown here as an example on the right-hand side. So for some satellite data, you have a lookup image, and it shows you, or it tells you, which pixel of your data is placed on a grid, and then you can kind of rectify your data with that lookup image. This is implemented in that function. Then we have subsetting. In there, you can select a certain spatial area or like temporal range. And then we have masking, where you mask your data according to certain, for instance, scene classification. And today in our example, we will see resampling, subsetting, and masking. Coming to the XCUBE server, as I told you, it's a set of RESTful web APIs. And using these APIs, a client then can access the configured XCUBE dataset. It can access the metadata, the coordinate data, and also the variables and their metadatas. Then we can extract time series for a certain geometry. We can also calculate the statistics for a certain geometry. The client can get the spatial image tiles, also as OGC WMTS. We can browse our retrieved data sets according to the OGC Stack API. We can perform computations on the data set, which then will be just executed on the fly and presented dynamically. And we can retrieve coverages using the OGC API coverages. Coming to XCUBE Viewer, here on the right-hand side, you see an image of how Viewer can look like. So the XCUBE Viewer is an application to visualize and explore the data cubes, basically, and it's placed on top of the server. So the XCUBE Viewer can then be deployed as a standalone web page, as shown on the right-hand side, but it can also be used interactively in a Jupyter Notebook. Here's an example which I will skip, so we have more time for actually looking at our data, which we're going to generate later. But the main functionalities are visualization. We can add multiple data cubes with multiple variables, which will be selected by the drop-down menus. And we can compare variables by viewing them side by side and having a slide bar, and then really have two variables next to each other. We can visualize dynamically generated variables, which are computed just on the fly. We can show time series for a certain point, polygon, or circled area. So we could visualize the time series of that circle, and we can also calculate a histogram, as we see here on the right-hand side. So that histogram shows the values of that circle. All of this we will see later at the end of our deep dive. So this brings us to our second part, which is the actual deep dive. For this, we want to use Sentinel-2 Level 2A data, which we get from the Sentinel Hub, and we use our plugin XCUBE SH. And we select the greater region of Hamburg, for the month June 2019. Then we will calculate spectral indices based on the spectral bands, and we calculate the vegetation index, the moisture index, and the maximum chlorophyll index. As a second data set, we then use land cover classification, which are provided by the DeepESDL platform, and then we mask the spectral indices according to different land cover classes. And then at the end, we will visualize and explore our data cubes in XCUBE Viewer. So for that, we have 6 steps to go through. So first, we access the data. Then we resample the land cover data to the grid mapping of the Sentinel-2 data. We write the data to the AWS S3 team storage, so we have it easily accessible. Then we calculate the spectral indices. We mask the spectral indices according to the land cover classes, and then we will view everything in the XCUBE viewer. So for that, we import all needed Python packages. This will take a few seconds. I won't go through that list. I will better talk about the next part, which we can execute now as well. So in here, we opened up a Dask cluster, which basically extends the computational capabilities of your Jupyter Lab, which we have here. And the cluster reproduces the Python environment on each worker. So here we select 4 workers, and then it automatically creates processing graphs without any explicit user interaction. That basically means that you can do large-scale data processing executed from your Jupyter notebook as a user without any specific engineering knowledge. The setup of the cluster is implemented in XCUBE, and the client we get from Dask. So this will take a little more. I will just continue talking and come back. So in the next step, we select our area of Hamburg. So we just define a B-box, which then will be plotted here. In the next step, we load our Sentinel-2 data from the Sentinel Hub using the XCUBE SH. For that, we use our function new data store. This will generate a new XCUBE data store, and we want to have a Sentinel Hub data store. And with that data store, we just open the data where we add the data ID. That's the Sentinel-2 level 2A data. Here you select the variable names, which are the different bands, the cloud probability, and also the scene classification. Then you put in your B-box, your spatial resolution, which is given in degree. Here, because of the projection, that would be around 20 meter, our time range, and then our tile size, which is your spatial tile size. The spatial tile size, basically how the data will be chunked. So how far are we? Not done yet. It doesn't matter. I can explain you here already the chunking. So the chunking you have for each time step, you have one chunk basically, and then on the spatial side you get the tile size, which you put in here. One note here: when you open it, only the cube structure is basically present, and also only the metadata is not the actual data is loaded. The actual data is just loaded on the fly. For instance, when you plot or when you write to another source. But in here, you can explore basically the data structure. Here you see the chunks, you see how big the file is, you get your metadata, and so on. So this is very convenient. Now we have our dashboard, which we will show later. So this is executed as well. So we select the greater region of Hamburg. Not sure if this has been run already, but we can just rerun it. It is also very quick because it's only the metadata. And now when we plot, for instance, band 4 for the last time step, then this will take a while because the actual data is loaded, and then we can also look at the task cluster. Here you see 16 task streams because we have 4 workers. Each worker has 4 virtual CPUs. And I mean, it was a very quick operation because it only plotted like the small image. But of course, when you write a big data set, then you could look at it for multiple minutes and see what is going on. Then a little excursion on the data store framework, because sometimes you don't really know what to put in and what's the data IDs and so on. And basically, the data store frameworks gives you a certain set of methods such that you can somehow extract the data and navigate yourself through the data store. So for instance, you can list your data IDs, and then you see here the different data IDs, and you see Sentinel-2 level 2A data. Of course, this then comes from the Sentinel hub. Then you can describe your data. So you get your B-box of what is available, the time range of Sentinel-2 L2A data, the data variables, and so on. And you can also get the schema how to open the data. So these are all the available parameters. And here you see the required parameters, which needs to be given. Otherwise, it will throw an error. Okay, then we can close this. As a next step, we then load the CCI and C3S land cover map from deepESDL S3. So for that, we take a new data store, which will be an S3 data store, and the root will be the bucket of the AWS storage. And then we just load the land cover, which has been placed there. So this land cover map is in a XCUBE levels format, and that levels format represents multi-resolution data sets. So some of you might know image pyramids with different resolution, and the levels format is basically a data pyramid where each level has a different spatial resolution. This is very helpful later for the viewer when you zoom in and out, such that you have a fast access to the data and a fast visualization. Okay, and then as a next step, maybe I explain the land cover classes. So the most interesting data variable is the land cover classes. And here you see the flag values, the flag meanings, and also some colors, which we use for the color mapping later. Now we can subset our data. So we select our bounding box, and we select the year 2019 because the land cover classifications are produced once a year. And since we have Sentinel-2 data from 2019 June, I just selected 2019. Then we can use a class called maskSet, which is implemented in XCUBE. And this can be basically used for categorical data sets. And this will give you, resolve basically the flag names and the values, and then gives you an easy access to the different classes. I just plot that such that you have the link between numbers and flag names here. And then we can create our land cover classification, where red is urban, for instance, dark green is forest, needle tree, I think, and the orange here is grassland, for instance. The color map at the moment I built in here from the actual colors given in the attributes. It is planned that this will be implemented in XCUBE soon-ish, or soon, hopefully soon. As a next step, we resample the land cover data to the gridded mapping of the Sentinel-2 data. So the land cover data has, the resolution is about 300 meters. For the Sentinel-2 data set, it's 20 meters. So we upscale the land cover data set. And this is done with this function, resample in space, where you put in your input, which you want to resample, and then you give a reference data set, which is our Sentinel-1. And then we just use the LenCover class data variable and put that into our data cube, which is then shown down here. As further information, there's a class called grid mapping, and there's a method which is called from dataset. With that, you can easily get more insights into that grid mapping, and also that class is heavily used throughout XCUBE. Here you see, for instance, that you have your CIS, your spatial resolution given in degree, and so on. The same can be done for the Sentinel-1. Okay. Then as a next step, we write the data cube, which we produced up here, this one here. So we have our different bands and our land cover classification on the same grid. And now we write this part to our AWS S3 team storage. So when a team is created on DBSDL, that team automatically gets a S3 team storage, and this can be used to save data, basically. All the credentials can be read out from the environment variables as shown here. And then we create another data store, which is a S3 data store again. Here we put in our bucket, and in storage option, you put in our key and secret. And we can initiate that. And then we would write the data, which I've done yesterday, which we're not doing today, because the data cube is about 15 GB, which took me about 20 minutes. And here, of course, you can also use that the method list data IDs to actually show. So yeah, we will use this one. This is the full one. The demo one is just like a half-written one, which I executed later. So as a next step, we load that data cube from our team storage, and then we calculate the spectral indices. So this is also just done on the fly, and the actual calculation will be done later. The computation of the spectral indices is done here in this function. So we just extract the different bands here, and then all these spectral indices are just linear combinations of some bands. So for instance, the moisture index is calculated here. This part is just metadata or attributes. Then we have our vegetation index here and our chlorophyll index, which is slightly more complex, but not really. And then we just create a data set and return that. And this we see here, we have our 3 spectral indices. Then as a next step, we use the Sentinel-2 scene classification to filter out all non-data flags and so on, and also clouds. So we filter out no data, saturated, and effective, and these are all the cloud groups. And here you also see like the value of a mask set, because then you can easily work with like human readable flags basically for the filtering. And then as a next step, we use our land cover classes and filter or mask our different spectral indices dependent on 3 classes. And here I use the tree, needle-leaved, evergreen, closed and open, urban and grassland, because these are the 3 biggest groups I found in my image or in the greater area of Hamburg. And so we go through the spectral indices and we go through the categories, and for each spectral indices we just mask it with where here in the back. And what we produce is, so we have our 3 spectral indices, and then we have our spectral index, moisture index, for instance, for the 3 classes, the vegetation index for the 3 classes, and the chlorophyll index for the 3 classes. Okay, and then we can visualize one example. This takes a while because we are on a grid of 20 meters now. So yeah, basically you could also plot in a lower resolution using the levels format. And then we also plot a histogram, and then we would write that data set to our team storage. So here we see the moisture index for urban, basically. And then down here we see the histogram of the data shown in this image. And then we would just write the produced data cube to our team storage with the method write data again, and then we can list our team storage where we have Hamburg cube from before, and this one we have written here, and the rest are just little samples which I used while setting up this notebook. And then we shut down the cluster, the DAS cluster, because it's a paid service, so you should always try to shut it down at the end of your notebook. And then at the end, we can visualize everything, what we have. So for the visualization, we use XCUBE Viewer, and the XCUBE Viewer uses some kind of config file, which is stored in a YAML, which I will show here. So in that config file, you need to set up basically the data cubes you want to show in the viewer. So we have an S3 storage. These are just the store parameters. And then we want to show the Hamburg cube, which is our Sentinel-2 data. And we also want to show our spectral indices, which we calculated. And then down here, you can configure a certain style, basically. So for each data variable, you can add a color map, and you can also add a value range of that color map. And this I've also done for the moisture, like for the different spectral indices. You can also configure an RGB if that is available in the data, where we use the red, green, and blue band, basically, of the Sentinel-2 data. And yeah, that's basically all for the config file. Oops. Okay. And then we can basically load that config file, initiate a viewer with our server config, and then show the viewer within the Jupyter Notebook, which is sometimes a bit small. So I will just switch to the web application where you just type in viewer info. You get a temporary URL, and then you see it in, as a full screen one-page web application. Okay, so first I would like to show you the different layers. So here you see the different layers, and you can opt in and out, and they're basically lying on top of each other. So for instance, I can opt out the base map, and then we would just have a white background. Here we can remove our data variable and view the RGB image, for instance. Then we can add overlays, user-based overlays, which can be configured here. So you can add an overlay here. Here's an example of the network of like the water network of Hamburg. If you put that in here, then we can put in the actual water bodies. Add that, select water bodies, And now we actually see the area of the water. You can also select other shapefiles and put that into a viewer. Another possibility would be, of course, to add a place or like a shape via some text or GeoJSON, and then you would get a drop-down menu here with different places, which you can also view in the viewer. Okay, regarding the data variables, so we see our two data cubes here. Here the spectral indices, for instance, moisture index. But we will stay first with the Hamburg cube, which are Sentinel-2 data. You can select the different data variables. What else did I want to show you? Right. Then you can change the different color maps. For instance, like this. You can also change your scale. There's a bad scale. Let's just go to 1. Okay, and we go back to 0.5 as before. And I select like a grayscale again, just that it's consistent. Then you can compare two variables. So you click here on the two variables comparison button. Then you see here with that #2 that this will be a second variable, and then for instance we can select scene classification, and then you can slide here back and forth. So if, for instance, if we here you can select the time range, and if for instance we have an image with like a lot of clouds, then you actually can nicely see that you have clouds here on the left image, and then these are classified as clouds in the data product, and compare it. Of course, you could compare now two spectral indices of a certain area. We can zoom in, and I would say it is fairly quick, and this is because we use that data pyramid, the levels format, so it just drags out one layer which fits to the resolution and accesses that layer. Okay, next. Okay, we remove this one and we go back to this. I will show you the full data cube again. I will go back to nice image where we don't have any clouds. Then here you have an info panel. This will show you all metadata of your data cube which you view at the moment. Here's even more metadata. And what is also nice is that it will give you a little snippet. So when you see something in the viewer, do your exploration, and now you want to have the actual data, then you can use that snippet to access the data. Info panel compare. Okay, and now we go to spectral indices. So the chlorophyll index is just shown here for water because I've filtered it for water when producing the cube. But let's go on to the moisture index. So what we can do is basically we can take a circle. You could also just draw a polygon with this button or take a button. And then we can add a time series for this circle basically. So this will show you a time series for the selected area. It will take a while because the chunking, if you remember, is that each chunk is one how's it called? One timestamp or one time step. Like if you have a lot of data, it would make sense to have a chunking where you have multiple time series, multiple time steps in your chunk basically, and then also this production will be faster. Yeah, it shows you the mean, but also the standard deviation. And then there's also one mode which is called statistics. So, for instance, and then you can produce the statistics by pressing this plus button. And what I would like to show you as an example is, for instance, we take our grass area, grassland, with that mask grassland. Then we calculate the statistics. So we have better view. Then we can use urban and calculate the statistics, and we can do the same for our tree area. And like that, okay, now, okay, and like that you see it better. Yeah, like that you can easily produce at least some kind of statistics and get a nice insight on the 3 different classes. Okay, that is all for the viewer.
Maybe, Konstantin, just to add, you showed this for the circle, but of course you could also calculate these statistics for any shape you imported, for example. So for any shapefile, arbitrary ones. So if you have administrative regions or whatever shapefile you may have for your analysis.
Right. Yeah. Of course, well, there's also an alternative to start the viewer via the Python API. So for that, you would need to load your 2 data cubes from the team start. Then you initiate a viewer, and then you just add the 2 data cubes to your viewer, and then you will get the same result as before, except that you don't have your config files. So you don't have color maps, which has been pre-configured by the user, and then you would need to do it by hand, which is possible. But yeah, so this is an easier access, but of course the config file will give you some standardization if you work in a team. Okay, that is basically all from my side.
Okay, thanks a lot, Constanta, for this nice overview of the different components and what you can do with XCUBE and DPSDL. If you have any questions, please write them in the chats. I don't know if there were any. In the meantime, I have a question. So when you use Sentinel Hub API, you have access to all the data collections available on Sentinel Hub, or a subset specific data collections?
Gunnar?
Yeah, to all. We simply, what you see here, you see this at the URL, we are in DeepEastDL, and for this team, there's also Sentinel Hub access configured, and then you have the same data offer you have with the API. And of course, you don't get the single products, but we already started with the analysis-ready data cube. So you basically forego all this data handling that you would have when you started with a individual products, downloading, putting them together.
Okay. And does XCUBE server support OpenEO?
Not yet fully, because that has been developed both approaches independently of each other. So I would say XCUBE is more on this pure Python world, and you can start the XCUBE server, but this is running on your own resources. It's not a service that we offer as OpenEO as a processing service, for example.
Yeah.
Everything you've seen here also works because everything is open source except for the Sentinel Hub API. It's a commercial service, but everything also works on any local machine. You can simply create this environment, open it, run it, have the server and viewer at home at your laptop if you like.
Okay. So we have a few questions. What exactly does rectifying in the XCUBE data processing?
So for more information, you could go to the XCUBE documentation. There's the algorithm explained, and the example which is shown is Sentinel-free, where you have a lookup image which shows you the distortion of the pixel location, basically. And then you apply that lookup image to actually rectify your data to the right position.
In that very example, you go from satellite coordinates to a regular grid.
Next question, is it possible to deal with data in non-regular grids? Let's say reduced Gaussian grids.
Gunnar, can you answer that?
I would say yes. So you may have to rectify it because that was the previous question actually, where you have a non-regular grid and then you rectify to a regular one. In any, let's say, any supported CIS, we can handle all of these cubes. So we had this Lat-Lon example, but there are also, of course, any other CIS.
Okay, and okay, that answers your question, Patrick. And someone is asking if it's possible to access the notebook later.
Sure. So we will publish this within DeepECL. There's a notebook catalog also with let's say single task notebooks explaining these steps individually. It will be also there. We can also publish it on GitHub so that people can have a look. So there's a repository for DeepECL.
Okay, can you share the link for the repository, Gunnar? We share it in the chat right now. I can find it. And someone is asking if there are any example notebooks using MEMS data.
Which data?
I shared it in the chat, the link for the GitHub repository.
CMEMS, yes, sure. That's a great question. The CMEMS store is a very nice one. So we have a full integration of CMEMS. So basically, you access by name, and then you can get all CMEMS data immediately. They just renewed or refurbished their API, so that's even with a better performance now.
Oh, but as far as I understood, if there's a notebook as an example, and there is one on GitHub in the XCUBE CMEMS example notebooks, which is then linked in this notebook here.
Yeah, I just pasted the DeepECL GitHub repository, and I will also do so with the XCUBE ones where a lot of example notebooks are.
Okay. So if there are any questions even after the session, we can always can send them directly to Gunnar and Constantin or via us. We were happy to answer them offline. So Gunnar just sent also the GitHub repository for the for XCUBE example notebooks. Perfect. Okay, maybe we go straight to the NOR portal demonstration, Federico, and if there are any questions, we can also take them at the end of the session.
Okay, perfect. I'm going to share my screen. Can you see it?
Yes.
Okay, thanks. So, how to access the providers and services available through the network of resources. First of all, you need to reach the Network of Resources portal by going to the nor-discover.org website, and you will find some information about what the Network of Resources is and all the different services that are available through the NOR. If you scroll down already the home page, you can find some useful information about, for instance, the number of approved projects, the providers onboarded inside the NOR, and more information. You can also go to the news sections to have an overview of what are the latest updates related to the network of resources, for instance, the latest providers onboarded and so on. And if you go to the outreach page, you will see all the previous sessions of the NOR webinar series. So also this session will be uploaded inside this page, and the video will be available through YouTube. Then, by going to the portfolio page, you can access the portfolio where you have all the different services available to the NOR. By clicking on Access It here, you will be redirected to a new web page where you have all the different providers and services listed. Here on the right, you can search for them with a text search, you can filter them with different filters, or you can just scroll down. In this case, we are looking for the ESDL. Let's see. Yes, this one. So we have some details about the services and the provider are offering. We have a list of the available collections through these services and also a link to the provider desk. This is really helpful because we always advise you to contact first the provider if you want to ask for a sponsorship from ISA concerning the provider services, because one of the things that we want to check when you send the proposal are the reasons why you are asking for the specific services. Then, by going to the pricing wizard, you will be redirected to a new web page where you can start filling the form that is used to ask for specific services. First of all, you need to clearly state what's the project type. We have 4 different project types: commercial, research, pre-commercial, and educational. And only research, pre-commercial, and educational projects are eligible for ISA funding. Then we have the list of all the services. We can select the services we are looking for by clicking the tick box, and we can also change the number of units and the duration, for instance, of the subscription in this case. Then, by going down, we will have an overview of the total cost we are let's say, requesting for all the services, and 2 different options. The first one is to directly ask the provider for these services by going to the provider website, or you can ask ISA for sponsorship. And in this case, you need to say, first of all, if you're working on an ISA project or not. And if you're working on an ISA project, of course, you will have an ISA technical officer assigned to you and an ISA contract number, so you will know it. Let's say we are not working on an ISA project, so we click no. And also, you have to decide if you want or not to co-found the cost. We want to remind you that there is a limit on sponsorship available for non-ISA projects, and usually this is around 5,000 euros. So everything that goes above 5,000 euros needs to be co-founded. But you, of course, can also co-found amounts that are less than 5,000 euros. Then let's say we are not co-founding the cost, and then we ask ISA for sponsorship. In this case, we'll be redirected to another web page, and we have the form itself, starting with the project title, then our name, the name of the project coordinator, the project coordinator work category, the official email address, This is really important, and we always stress out about this point because it must be the organization email address. We cannot accept personal email addresses like Gmail, for instance. Then the project organization name, country, webpage, and address. What you need to do after this is to write what are the project objectives of your project, the final goals, the implementation methodology that you want to use, that you're going to use to reach these objectives, and the expected results. Then, and this is why we advise you to contact the provider first, you need to write the justification for the selected services and provider, because this is important for us, since together with the description of work within the cloud environment, it tells us what you are going to do within the cloud and why you decided to work with the specific services. We want to remind you that the network of resources is an initiative aiming to bring users to data and not the contrary. If you want to access data, you can find other ESA initiatives, but in this case, we want to see that you are going to work within the cloud environment of the provider. Then you need to state what is the geographical area of interest of the project. You can, let's say, put a specific bounding box or saying that you're going to work on specific cities or regions and so on. Then, if it's the first time or not that you have applied for not sponsorship, if it's not the first time, you will need to indicate here the number of the previous request ID that you sent. And you have also to confirm that you have fulfilled all the duties and the commitments that you accepted by sending a sponsorship. For instance, we'll see it later, the set of slides that you need to send. Then, if you're working on a project here, there will be more fields related to the ISA technical officer, ISA contract numbers, and so on. And in the end, you will have an overview of the services you are requesting and the cost. Finally, the last things that you need to do are to indicate the expected date of submission of the set of slides in the order of month and year. And as I was saying, this is part of the duties that you have when you submit the request, because at the end of the project, we need to have a report done in PowerPoint or any PowerPoint-like software where you clearly state why and how the resources that you asked to the network of resources were helpful for your project. We don't need to see the final results or if you succeeded on your initial goals or not. What we need to see is how you use the resources to try to reach these goals. Then you can or cannot sign up for the newsletter. This is up to you, and you must accept the ISA privacy policy. Once you have done all of this, you can click Export Sponsoring Request. It will generate a PDF file. You need to download the PDF file, sign it, and if you are working on an ISA project, you need also to have it signed by the ISA technical officer. And once you have the document signed, you need to email it to nor-sponsorship-request@isa.int. It will then trigger the evaluation procedure that usually takes around 6 working days, but it might take also longer if we need more information, but in that case, you will be contacted. That's it from my side, so I give back the floor to you, Zainab.
Thank you, Federico. So if you have any questions related to the sponsorship requests, same again, write to us and we'll be happy to answer them. I see no further comments or questions in the chat. Maybe just a reminder that XCUBE is open source, so you have the links to the GitHub repository where you can find the codes and all the plugins. So you're more than welcome to report issues and contribute. And get back to Gunnar or Constantine if you have any questions for this session offline. Thank you, everyone, and see you very soon in the next training session. And just a reminder that at the end of the session, when you leave the webinar, you will have a form that we kindly invite you to fill in to help us enhance the training experience. And we hope to see you, for all the participants, in the next training session. Thank you so much.